Let's take a look at the process of firepower generation. This is a firepower generator. When generating electricity, workers will transport the coal from the train through the coal belt to the generator for the coal machine. The coal will be passed to the coal machine and flowed into the molding machine at the bottom. The molding machine will grind the incoming coal into powder. The fine particles of these grinded powders will then pass through the wind tunnel to the combustion chamber. Here, the coal powder will be ignited. The high-temperature heat generated is used to boil water. The first water comes from these pipes. The water will rise along the pipes and then come to the gas of the boiler. The gas of the gas can improve the efficiency of the boiler and save fuel. Then the boiler water will come to this gas package. The gas package can be separated from the water. The water passing through the gas package will then flow to the dense pipes around the boiler. It is called water cooling wall. The boiler water will fall along the water cooling wall. In the process of flowing, the boiler water will absorb the heat generated by the coal powder combustion. This produces high-temperature, high-pressure steam. These steam will then pass through the pipes and return to the gas package. These pipes at the top of the gas package are the steam pipes. The steam is shown in red. These separated high-temperature, high-pressure steam will then be sent to the overheating chamber for further heating. Here, the steam will slowly change from saturated to overheated, but the temperature of the steam is still not enough. Therefore, the steam will be sent to the second overheating chamber for further heating. There are several pipes to the outside of the overheating chamber. When the specified temperature is reached, the overheated steam will flow along these pipes to the main steam release valve here. The release valve can adjust the flow of steam to the steam engine. In an emergency, the release valve can completely stop the flow of steam. Then the steam will come to the second valve. These valves are controlled by the automation system of the power plant. They can quickly respond to pressure and temperature changes to ensure the safety of the equipment. Then the steam through the valve will flow through the steam pipe to the gas engine group. There are three types of gas engine groups. They are high-pressure gas engines, medium-pressure gas engines, and low-pressure gas engines. High-temperature, high-pressure steam will first flow through the pipes above the high-pressure gas engine and enter the inside of the gas engine. At this time, the pressure of the steam has reached 178 and the temperature has reached 540 degrees Celsius. After the steam enters the gas engine, it will expand rapidly, thus promoting the high-speed rotation of the gas engine. The speed can reach 3,000 revolutions per minute. Let's take a closer look at how the gas engine works. This is a small windmill. When we use the steam generated by boiling water to blow to the small windmill can rotate quickly. If we replace the small windmill with a gas engine blade, the blade can rotate as well. But there is a problem. A single set of blades will cause a lot of steam to flow. In order to solve this problem, we can add another set of electronic blades and a set of rotor blades. The electronic blade does not rotate, but only changes the direction of the steam. When a lot of steam comes in from the side, it hits the electronic blade. After the steam changes direction, it comes to the rotor blade and produces upward thrust, driving the rotor blade behind to rotate. In order to ensure that the steam can be fully used, we can add more rotors and electronic blades, thus generating more power. If you look closely, you can see that the rotor blades are very similar to the wings of an airplane. The top is longer than the bottom, so the steam flows more along the top. At the same time, more distance must be moved, so the top steam flows faster. The faster the flow, the smaller the compression. This causes the pressure below to be greater than above, generating upward thrust, thus driving the rotor blade to rotate. This is actually the bottom principle of the gas engine. But there is a problem. After the steam hits the electronic blade, it loses energy, causing the pressure to drop to only 85 bar, and the temperature to drop to only 340 degrees Celsius. Therefore, in order to improve the efficiency of the steam again, the finished steam will then flow out through the steam pipes at the bottom of the high-pressure gas engine. These steam will be sent to the heaters in the boiler to be reheated. Like a boiler, there are also many heaters. They are located at the top of the boiler. After the main heater is heated, the steam will come to the second heater and continue to heat. When the temperature and pressure are reached, the steam will flow out of the boiler through this yellow pipe. Then, along the pipe, the steam will first come to the heating valve of the gas engine. Like the main heating valve, the heating valve can also control the flow of steam into the steam engine. It has a valve inside. When the power demand is low, the valve will partially close to limit the flow and pressure of the steam. When the power demand is high, the valve will be fully open, thereby maximizing the flow of steam. After precise control, the steam will then enter the next gas engine, which is the mid-pressure gas engine. Like a high-pressure gas engine, the mid-pressure gas engine will rotate at high speed through the high-temperature, high-pressure steam. After the completion of the steam, it will come to the low-pressure gas engine. The steam of the low-pressure gas engine has lost most of its pressure and energy, but it is still enough to drive the low-pressure gas engine to rotate. After the steam passes through the high-pressure, medium-pressure, and low-pressure gas engines, the heat will be converted into mechanical energy, thereby driving the rear generator to generate electricity. Next, let's take a closer look at how the generator generates electricity. Let's take a look at an experiment first. This is a coil. The coil is connected to a current meter by a guide line. When a curved magnet is used to move back and forth in the coil, the magnet of the current meter will also move back and forth. This is because the coil will cut off the magnetic field of the magnet, thereby generating inductive current. This phenomenon is called electromagnetic induction. The underlying principle of a generator is actually electromagnetic induction. Generators are mainly made up of two parts, a resistor and a rotor. But the difference is that the rotor of the generator does not use the neodymium magnet mentioned earlier. You can imagine that such a large neodymium magnet will be very complicated to install in the slot of the rotor. Even if it can be installed, as time goes by, the magnetic field of the neodymium magnet will also slowly decrease. So how do we solve these problems? Let's take another look at an experiment. This is a coil. After the two ends of the coil are connected, magnetic field is generated around the coil. This coil is an electromagnetic magnet. This kind of electromagnetic magnet is not much different from the common conductive magnet. The only difference is that the magnetic field will disappear after the electromagnetic magnet is cut off. If the voltage is increased, the magnetic field will continue to increase. Generators actually use electromagnetic magnets. It is made up of 4 sets of coils. Since the electromagnetic magnet does not conduct electricity at first, it is very convenient to install. All you need to do is to wrap the 4 sets of coils around the magnetic field of the 4 protrusions. This kind of coil combination is also called the magnetic field loop. The loop wants to generate the magnetic field and needs to be charged. So there's also a direct current source here. The direct current source is connected to the 2 rings of the coil through 2 inductors. In this way, a very stable electromagnetic field can be generated around the group. To make it easier to explain, now let's take out a group of electromagnetic coils. When the magnetic field of the coil is cut off and the electromagnetic field is around the group, according to the electromagnetic induction law, the electromagnetic field around the group will produce an inductor. When the end level of the coil is in this position, you can see that only a very small amount of magnetic field is cut off and the electromagnetic field around the group. But with the rotation of the coil, the magnetic field of the cut-off electromagnetic field around the group is getting more and more. The waveform generated is as shown in the picture. When the coil continues to rotate, the magnetic field of the cut-off electromagnetic field around the group decreases again. The waveform generated also begins to decline. After a quarter of a circle, the S level comes to this position, but the magnetic field is opposite to the previous direction. So when the coil continues to rotate, it will form a waveform opposite to the direction. This is also the exchange point we often talk about. Now let's add the other 2 groups of electromagnetic field around the group, and the angle of the 3 electromagnetic field around the group is 120 degrees apart. In this way, when the coil rotates, we get 3 exchange points. The electromagnetic field around the group of the same generator uses a star-shaped connection. 3 of them connect to the flame of the 3 exchange points. The other 3 groups of electromagnetic field connect to each other at the end of the group, form a neutral line and connect to a zero line, and then put these devices into the electromagnetic frame. A generator is assembled. When the coil rotates at high speed, the generator can generate electricity. But there is a problem with this kind of generator. There is a big gap between the 2 magnetic fields. It is called the gas phase. If the coil rotates at high speed, the gas phase will cause the magnetic field of the generator to increase and the efficiency of the generator to decrease. Therefore, this kind of generator is generally used for firepower generation. It is the same principle as the generator mentioned earlier, however the coil is cylindrical. There is no protruding magnetic field, the length is longer, and there is no gas phase, so the coil can rotate at a higher speed. In addition, the longer coil will also produce more magnetic field. So the generator will produce more electricity. This electricity will then be transported to the voltage regulator for compression. After compression, it can be sent all over the country. After knowing the principle of the generator, we go back to the low-voltage steam locomotive. The steam that is completed in the low-voltage steam locomotive will not be wasted. These steam will leave the steam locomotive, then enter the coolant at the bottom of the low-voltage steam locomotive. The coolant is filled with circulating coolant water. Therefore, the steam pre-coolant will liquidate into water. Then collect the liquidated water through the collector at the bottom. Because when the coolant cools the steam, the water in the coolant pipe will heat up. Therefore, the temperature of the coolant water will become very high. In order to cool down, the coolant water will be sent to the cooling tower for cooling. Let's take a look at how the cooling tower cools the water. First of all, the high-temperature cooling water will enter the cooling tower along the hot water pipe. The cooling tower is made of mixed clay materials. Generally, the height can reach 200 meters. The inside of the cooling tower is not complicated. It is mainly composed of a tower basin, a vent, a heat-dissipating filling, a water pump, and a water dispenser. The hot water will first come to the water pump through the water inlet. After that, the hot water will come to the heat-dissipating filling. The heat-dissipating filling can extend the retention time of the coolant water to ensure that the coolant water has enough time to exchange heat sufficiently. After that, the vent below will suck in a lot of natural air from the outside to cool the high-temperature cooling water. After cooling, the coolant water will go through the water outlet pipe at the bottom. Back to the freezer for the next cycle. You may find that the cooling tower is generally designed to be narrow in the middle. This design can make the natural air after cooling the water. It can accelerate the upward flow and quickly bring the heat out of the tower, because the coolant water will freeze into a tiny drop. Therefore, we often see a lot of white smoke coming out of the cooling tower. That is not a harmful waste gas, but a water vapor. Let's go back to the freezer. The frozen water from the freezer will then flow out through these pipes, then all the way up to the low-pressure heater above. The low-pressure heater can preheat the coolant water in order to improve heat efficiency. At the same time, it can prevent the coolant water from entering the boiler directly, causing the boiler equipment to be damaged. The coolant water after heating will then come to the dehumidifier here. The dehumidifier can also heat the coolant water. At the same time, it can also heat the water to a saturated temperature. Remove the oxygen in the water and other gases in order to prevent the equipment from corrosion. After the coolant water is processed, it will go through the pipes, enter the inside of the boiler again. The next step is the same as before. The whole system will enter the next cycle. It should be noted that the boiler will generate a lot of waste gas. These high-temperature waste gases will pass through the dehumidifier first, in order to preheat the water inside the dehumidifier. As the waste gas heats the water, the temperature will also drop, in order to improve the heat efficiency of the boiler. This is also the basic reason for the dehumidifier. Passing through the dehumidifier waste gas, then it will come to the waste gas processing equipment along the pipe. This is a dehumidifier. Through the dehumidifier in the reactor, make the quencher and high-temperature waste gas react in order to reduce the emission of carbon dioxide. The finished gas will then be sent to the dehumidifier, because the dehumidifier has a positive electrode, and the dehumidifier of the dehumidifier has a negative electrode. According to the one-level vacuum principle, the dehumidifier will be absorbed into the dehumidifier. At the same time, the dehumidifier will also vibrate at high frequency. In order to attach the dehumidifier on the dehumidifier, shake to the bottom of the shaking. The dehumidifier in the reactor, the dehumidifier after the dehumidifier. Then it will come to the next device. That is the dehumidifier tower. Here, the dehumidifier and water, and the dehumidifier will react. The reaction will remove the carbon dioxide in the dehumidifier in order to reduce atmospheric pollution. After the dehumidifier tower is processed, the dehumidifier, it can pass through this more than 100 meters of chimney to the atmosphere, and after the dehumidifier, there will be a lot of castings. After these castings are processed, it can be used in the field of building materials, agriculture, and industry.